linear. And this is advanced compartment masonry, which I worked some years ago, maybe 15 years, 20 years ago in this particular area, where I thought about what you call the interface element. So you got the masonry interfering with another element completely different in material and completely different in strength. So therefore, there is an interaction, what you call of an element, could be included in the, what you call in the finite element model. And it can make a huge difference compared if you consider it as fixed or pinned. And this model, I used it in order to understand how the fire is affecting the stability of the building in relation to fire spread from one floor to another floor. And you can see that publication is available if you want to download it. And if you don't have any particular questions, you can come back to me. And of course, I can answer, and there is no issue on that. Other work has been done just recently to understand the thermal conductivity of the different block to another block before they implement it in the finite element. And of course, and run all the three models of the wall and see the temperature distribution in the boundaries, and of course, the deflection as well. And of course, the testing procedure has to be to the standard, because there is a conflict how the loading will be placed on the wall between a code to another code. There is an engineering evaluation in relation to the insulation and the load-bearing criteria. And I think there is quite good, what you call, correlation between the advanced model and the experimental model. Well, I come with the conclusion here. I know there is a lot of work should be done in the particular masonry because it varies from country to country. The lesson from real fire in real buildings, so we have to learn from that. If we don't consider that, we're still playing in the lottery and we don't know where exactly we're going. So we have to define the real parameters, what happened in the real fire scenario. Full or large scale fire test. This is very important. The data collected for that can solve a lot of problems, and the protocol to create the code can be justified. If you don't have this, it can be very difficult to convince anyone about the code you want to implement. Well-instrumented and designed small-scale fire tests if you want to. You have to put the right instrumentation because the data is valuable data if you don't consider some other things. Material investigation, use of smart technology. You have to implement technology in order to have very important data information. Example, golden gauges give you the heat flux. You don't see it, but you can feel it. Example, if there is a fire in the compartment, you do have windows. At certain time, the heat, you cannot see it, but if you cross it, it can burn you. And that's what you call heat flux. So heat flux has to be sort of recorded by the golden gauges. And this is very important, what you call instrumentation. Robustness of building regulation. So we have to look at the regulation where things do not go well and how to sort of implement the knowledge and how to sort of implement other things not considered before. More robust and safer design. Validate computer software because the computer software could be not in the right way. Validate design methods as well, which is the prescriptive approach or the performance approach. Allows option, this is not considered here at the moment. Option design to be determined, taking into account the life safety, the financial impact, and environment issues. This should be included in the design, which we don't include it at the moment. Now, how fire engineers interact with other members. This is very important. The fire engineer usually gets something from the architect and some information from the structural engineer. And of course, there is a code has to be followed by the structural engineers. And of course, the fire engineer has to follow the data and get some information from the architect and the structural engineer. So it goes to solution. That solution, you can see the role of the fire engineer is the, what you call, the main person to decide if it can be applicable or not. So, but sometimes, if there is a solution satisfied with the element, minimum requirement of fire resistance is good, that's fine. But sometimes we don't go to the right point. So here we'll be completely lost. The code stopped somewhere. And what should we do? So you can see the line here. This is the level of understanding the code at certain level of the structural engineer, fire engineer. Now, there are some people doing what you call master and PhD, but at certain time they become specialists. And one becomes specialist, at least you spend maybe 15 years. And of course, you do have the, what you call professional engineer, or in England we call it the chartered engineers. So you control the full design, the full team. What you have here, you should have the structural knowledge. You should have the research together in order to become in that boundary of understanding the fire at very advanced one. And what you do here, you bring your expertise and you try to create a CPD course, continuing professional development, and you bring this team and try to provide an approved document, not existing in the code, but can satisfy the will, what is requested by any project whenever it is very complex. And the same thing here, you can bring some equations, and you can also, this equation can satisfy the group, and of course, you can solve the problem. There is a CPD which I'm doing in Ireland on the 23rd of November, and of course, to teach the new concept of design and standing fire from localized fire in relation to vertical element, which is not considered in the Eurocode. What I can say, this is what I want to say to you. This is what they use in the Eurocode. This is the Hesketat model, and this is what we call the Hasimi model. There are two models used, with, you can see the names are Japanese, okay? And are used in the Eurocode. But they don't consider the vertical element. And that vertical element can be wall and can be masonry. And up to now, it is not considered in the Eurocode. There is a research completed in relation to steel column, which I completed that, but not in masonry. And this is the right way to go. There's no need to waste time. And I believe this is the next step to be considered to develop the Eurocode, or even the code in any part, what you call in any country. This is a test which I conducted some years ago to develop Eurocode 2, which is an annex. We cannot develop the code all, but a part of the annex. And you can see it's real fire. We came to the stage to do a real fire scenario, and from there, you can see how we have to learn the traveling fire. The traveling fire is not considered in Eurocode. This is another challenge. This is the reference of the work of today, coming from my own publication, the design code, and the lecture of my MSc fire, which I do in Ulster University. In Ulster University, we do have the most, what you call, facilities existing from the SBI, burning item, the 20 megawatt. This is, we can build here 2-3-story building under the big hood, and the hood can give us the heat release rate, and we can do furnaces, and we can compare what happened in the furnace, what happened in the real fire. So on the other side, we can learn the chemistry, the TGA, FTIR, the gauze, and the gases, and coming from the specific, what you call a characteristic of the material you test. So you have to understand the physics and chemistry before it comes to the engineering application, which is the cone colorimeter. And from the other side, this is our development, which is called the UFA, Universal Flammability Apparatus. It's unique, it's our idea, which means the sample is not open to the oxygen, but it's inside and mixed with other gases as if the element is in the rear compartment gases. Related to the mechanism of working, This is how it works, government, industry, and university. You cannot go on your own. You should have a partner in the industry, and you should have a control government to support the finance, and of course, to build up the regulation, to have a proper safety environment. This is the final slide, is a future fire safety management system. This is what is missing. This fire safety system has to be controlled by satellite, and every industrial sector or every museum, every whatever university or anything has to be sort of a recorded information and monitored by the system. And from here, we know exactly that the fire is taking place, and of course, the fire brigades has to go at early time before fire spread, etc. Because we are living now in a very mega city. It will be difficult to go to the place where is the fire, if there is, let's say, in Sao Paulo or New York or London. That would be very, very difficult. And thank you for your attention.
Thank you very much, Dr. Nadia. Obrigado. Bom, nós tivemos aqui uma palestra muito interessante do Dr. Nadia. Ele vai estar aqui amanhã também, né? Então, amanhã a gente vai ter um mini curso. A programação do mini curso está disponível ali na mesa de inscrições. E a gente vai ter a oportunidade de se beneficiar um pouco mais dos conhecimentos dele. Então, quem quiser ver essas coisas de novo, um pouco mais lenta, né, com um pouco mais de calma, a gente vai ter essa oportunidade. A gente tem um grande dia pela frente ainda e as perguntas da sessão da manhã vão ficar para o final da manhã. Então, eu gostaria de convidar todos agora para um coffee break que a gente vai fazer. A gente vai reduzir o tempo de coffee break para 15 minutos, voltamos às 11 e a gente continua com as palestras às 11. Muito obrigado.